Okay, so on the last really long video, we went through 4 different versions of base excitation. And for this video, what we're going to do is we're going to kind of finish looking at the response of a system, specifically, oh, hold on there. There we go. What the magnitude of the response of our system is as a function of all its inputs. Well, hi there, Fluffy. Hey, buddy, do you want to help do some vibrations? Fluffy's my dog. He's here. He's a Great Dane puppy dog. He loves vibrations almost as much as I do, which is to say a lot. Okay, so anyway, we're going to look at what the response of a system is as a function of various input parameters and system parameters, mass, natural frequency, damp frequency, etc. Kind of with base excitation, but we're going to make it really, really general, okay? Within the confines of a specific example, I guess. So what we're going to do is let's take a look at something that kind of has all the things. So here's a beam, and it's gonna rotate. So our degree of freedom is going to be theta, okay? And then it's going to have let's make our inputs blue. We've got a spring, and then a damper, and those are fixed. So there's K1 and C1, and then you know what? Let's right here. Let's put a rotating load FR due to some unbalanced mass M, right? That's operating at a distance E is eccentricity E at a driving frequency of omega. And then at this end right here, let's put another random f of t. Okay, I don't know where it's coming from. It's just an f of t that just exists from somewhere. It's magic. And then let's come in here and put another dash pot damper. And let's give it a base excitation, so K2, C2. Okay, so what we have, and then let's put some more dimensions. So this will be L1, this will be L, and they're all just spaced evenly L, because there's enough going on here, okay? So what we have is we have a base excitation, an external force, a rotating and balanced force, and then some other system parameters, K1 and C1, which are set to a fixing. So this is going to help. This is going to shift the MEQ. Whoa there, MEQ and CEQ. And then let's just make our lives easy. Let's say J exists, and J includes everything that we need to do. So this is pretty different from what we did before, which was largely things like this. Okay. And so that's what we were doing before, and I think as a group we got pretty good at it. So this is a lot more complicated, right? I don't know. Personally, I feel like we should cry, because look at all that stuff. There's no way we can do that. No, you all can do this. You've been doing great on getting your equations in motion. Okay, so we can do this, and we're going to do it together. Or I guess I'm going to do it, you're going to follow along, but maybe you can work ahead of me. So we know how to handle this in Lagrange. We know how to handle this in Lagrange and this, but let's talk about how we're going to handle these f of t's. Okay, we haven't directly dealt with those. So remember, Lagrange deals with energies, right? We've got the potential energy and the kinetic energy and the dissipative energy. Okay, and then we have these extra forces here, and these are what are called non-conservative forces. Okay, they're non-conservative because they're coming from the outside and they're adding energy in. Okay, so when we do our Lagrange, we're going to end up putting our non-conservative forces on this side of the equal sign. Okay, and since these are directly forces, okay, the energy of translation due to a force is just equal to F times the distance it went across, okay? And then energy due to rotation of a moment is the moment times the angle it went through, okay? Which would be equal to F times L, times theta, assuming that these forces are perpendicular to the length, which in this case they are. Okay, really, this should be, this should be F cross L vectors times that angle. Okay, and this is a vector, so this also would be a vector. Okay, but in this case, everything's perpendicular, so we can say F times L times theta. Okay, so for this one right here, this energy due to F is equal to F of t times, and then it's rotating about this point right here, so times 2L times theta, and the energy due to Fr is equal to Fr of t times L times theta. Okay, now we haven't yet defined what F of t and Fr are, so let's define that. So let's call F of t is equal to F naught cosine omega t, and Fr of t is equal to m, which is e omega squared sine omega t. Okay, so this comes from the section 4.7 on rotating imbalances. Please note that the rotating imbalance has a mistake in the textbook where it has this divided by 2. That's incorrect. As far as I can tell, it's incorrect at least. Okay, so there's our F of t, there's Fr. We're going to leave J as J, K1, C1. Those are all what they are. Okay, so let's go through and let's start our Lagrange process. So one thing I have yet to do is we've got to define our displacements. So we'll call that x1, x2, and we'll call x3, okay? So theta is equal to theta. Theta dot is equal to theta dot. So there's our degree of freedom. And x1 is equal to x1L. That's wrong type of L. L sine theta. And x1 dot is equal to x1 L cosine theta, theta dot. And x2 is equal to x. There's no x there. There's no x1 there. There we go. So, once you get in the habit of writing x's, you just want to keep on writing them everywhere. Okay, and x2 is L sine theta. x2 dot is L cosine theta, theta dot. x3 is 2L sine theta, and x3 dot is equal to 2L cosine theta, theta dot. Okay, so now we've got our geometry. Now let's take a look at what things we're going to have. So we've got the kinetic energy that's coming from J. We've got potential energy in spring 1 and spring 2. We've got dissipative damping in damper 1 and damper 2. And then we've got these other energy terms from F of t and Fr of t, okay? Okay, so let's write these out. Now, okay, so and I want this to be black. Okay, there we go. So Tj is equal to 1/2 j theta dot squared. That's easy enough. U1 is equal to 1/2 k1 x1 squared, which is equal to 1/2 k1, and then L squared sine squared theta. And then U2 is equal to 1/2 k2 times x2 minus y, right? So that's actually x3. Rookie mistake. Dr. Hildreth. x3. So that's this displacement minus this displacement. Okay. And don't forget to square that. So it equals 1/2 k2 times L sine theta minus y squared. Okay. And then, what's next? R1 is equal to 1/2 C1 times x1 dot square, which is equal to 1/2 C1. Keep on writing the curly L's instead of this capital L. L, and then this becomes L squared cosine squared theta, theta dot squared. And R2 is equal to 1/2 C2 times 2, getting ahead of myself there, x3 dot minus y dot squared, which is equal to 1/2 C2 of 2L cosine theta, theta dot minus y dot squared, okay? And then we have our energy terms. So E, the energy for the force, is equal to F of T 2L theta dot, which we can write out if we want. F naught cosine omega T times 2L theta dot. And the energy due to the force term is equal to, let's see, where's that one located? That one's located at L. So it's 2m omega, or E omega squared L theta dot. Oops, it's not theta dot. These aren't theta dots. These are just regular straight up thetas. Theta, theta. And this is sine omega t theta. Okay. Okay, so I'm going to copy this all over and to the next page. So we can do our Lagrange. Okay. Which is, of course, our favorite method. So I'm going to get rid of this stuff. Probably would have been faster just to rewrite it. Okay. And now we can move things over. Now that we've got that room. Okay. And then move everything down a little bit. There we go. Sorry, we just need this room back. There we go. Okay, so dt d theta dot, that just becomes j theta dot, and all these are zeros. And then dt d theta dot and ddt is j theta double dot. I know that's tedious for some, one little thing, but I really do believe that if you can find a process that just works for everything, then life becomes a lot simpler, even if it's tedious. And then du d theta, this we've done multiple times before. That's k1 L squared theta, okay? And then this one, let's just do that derivation together just in case we've forgotten. And it's always useful to do any of these more complicated ones. Is equal to 1/2 k2 of dl sine theta minus y squared dl sine theta minus y. Okay, so I'm just kind of working my way. We've got, here's a function, and then here's a function, and then that last one times dl sine theta minus y d sine theta times d sine theta d theta. Okay. And this process, as long as you write it out, it's not that hard. So this ends up becoming 1/2 k2 times 2 times L sine theta minus y, okay? And then times L, and then times cosine theta, okay? And that ends up being, those cancel. That ends up being K2 times L sine theta minus y times cosine theta. So that goes to 1, that goes to theta, and this equals K2 L squared theta minus K2Ly. Okay? So this is K2L squared theta minus K2Ly. Okay? Now, this next one, that takes care of that row. And now we have dr d theta dot. And this becomes C1 L squared theta dot. Okay? Let me write that a little bit neater. C1 L squared theta dot. We know that. And this has, this has the same form, but we've got this 2 here. So, and you know what? We are missing a 2 here. There we go. Where did we drop that 2? Yeah, because I didn't actually go back and inspect that and check my work. Okay, and are there any other... Okay. This f of t, there's our 2, and there's our singular 1. And why is that 2? Where's that 2 coming from? There's no 2 here. Okay. So I think I found, there's the 2, that's a 2, that's a 2, that doesn't have a 2. Okay, I think I found my mistakes. Phew. Okay. Now let's go and fix this. This becomes a 2, 2, 2. Okay, there's a 2, and there's a 2. And that becomes 4, and that becomes 2. Okay, let's check my other notes, see if there's anything else I forgot. Okay. Now, this is going to have the same form of C2, 4, and that's a 4, and that's a 2. 4C2L squared theta dot minus 2C2Ly, okay? And then dE d theta. This, of course, this doesn't, the only thing that depends on theta is right here. So that just goes back to the moment. 2L F naught cosine omega t, and this becomes, and let's get rid of that 2. Okay, and this becomes M E omega squared L sine omega t. Okay? So now we can go ahead and we could put all these together. Okay? So we end up with our equations of motion. Equations of motion is J theta double dot plus K. God, why does it keep on doing that? K1 L squared theta plus 4K2 L squared theta minus 2K2Ly plus C1 L squared theta dot plus 4C2L squared theta dot minus 2C2Ly equals, now these non-conservative forces over here, we're going to put them just right on the other side. So equals 2L F naught cosine omega t plus ME omega squared L sine omega t. Okay? Now we'll simplify this a little bit. Okay? So we've got J theta double dot plus, now let's do our theta dots. So we end up with, that's an L. C1L squared, okay, plus 4C2L squared, okay, theta dot, and then plus K1L squared plus 4K2L squared theta, okay, equals, okay, and that should be a y dot there. Make sure there's a y dot there, okay, equals 2C2L y dot plus 2K2Ly plus 2FL, that's the same form, 2L F naught cosine omega t plus ME omega squared L sine omega t, okay? Now, I know what you're thinking. Oh my gosh, this is so much stuff. Oh, what are we going to do? Don't worry. I'm going to walk you through this, and also don't worry. You actually have a really good foundation to know what to do. And after this video, you'll have even a greater foundation, okay? So, let's define our MEQ is equal to J. CEQ is equal to C1L squared plus 4C2L squared, right? Because we don't want it to keep writing all that over and over again. KEQ is equal to K1L squared plus 4K2L squared, okay? Now our equations of motion are going to start looking a little nicer. M theta double dot, our MEQ, plus CEQ theta dot plus KEQ theta is equal to all of this. Copy, paste, and okay. So we're simplifying a little bit just by saying, okay, here, this is our equivalent this is our equivalent damping coefficient. Here's our equivalent spring constant. Okay, now this side is looking pretty familiar. Okay, we're going to deal with this side in a second. So remember, we're going to define theta of t, right, our particular solution, is equal to capital theta. So I'm going to draw capital theta like that because I don't know how to draw capital theta. Okay, cosine omega t minus phi. Okay, so here's our phase shift right here. And that means that theta dot p is equal to negative omega capital theta. That's a capital phi. Capital theta sine omega t minus phi, and then theta double dot p of t is equal to negative omega squared capital theta. Like I said, I'm sorry, I don't know what a capital theta is supposed to look like. So I'm just drawing it like that to make that distinction. Okay. And then our y of t is equal to y cosine omega t, and y dot of t is equal to negative omega y sine omega t. Now, there's one thing I did do in this problem to make life easier, is all this whole system is all going at omega, and I'm assuming all those omegas. I didn't have any phase shifts in there. It's not too much trouble to deal with the phase shifts, but I don't want to deal with the phase shifts right now. And pretty much you deal with the phase shifts the same way we did in the earlier examples when we dealt with the phase shift here. Okay, where you apply that cosine of a minus b is equal to cosine a cosine b plus sine a sine b. You got separation of variables if you did want to have a phase shift. Okay, so now we're going to go in and we're going to put in these. Oh, that was supposed to be on this one. Going to put these into here and our y's. And it's going to look worse, but don't worry, it's going to get better. Okay, so now we have MEQ times negative omega squared capital Phi cosine omega t minus theta, okay, plus CEQ times negative omega Phi capital theta sine omega t minus Phi, okay, and let's get this room back so we can fit it all together, plus KEQ times Phi, capital Phi, cosine omega minus Phi, okay? And let's group the cosines together. So we end up having KEQ Phi minus MEQ omega squared Phi, or capital theta, sorry, times cosine omega t minus Phi, plus omega Phi CEQ, and let's make this the same order that I did all the others. CEQ omega capital theta times sine omega t minus Phi. Okay? Let's pull this to the next page, and we'll see what we're going to do here. Okay, and what we're going to say is we're going to let, because I don't want to have to rewrite these over and over and over again, we're going to let A equal, let's make sure I follow the same notation I was using before. Okay. So let A equal positive MEQ omega squared capital theta. B is equal to positive CEQ omega capital theta, and C is equal to positive KEQ capital theta, okay? So now this simplifies to C minus A cosine omega t minus Phi plus B sine omega t minus Phi, okay? So look, all we've done is we've done substitutions for what variables are called. MEQ, CEQ, KEQ, those are just long things. A is just a long thing. It's just constants, okay, just to save ourselves a lot of writing. And look, when we go and reduce how much writing we've got, it looks a lot less intimidating, okay? And then let's go in and take care of this side, okay? Okay. And like I said, this isn't hard, it's just tedious, and you know, who doesn't love tedium? We do. We love tedium. Okay, so now we can put this as 2C2L, and y dot was negative omega y sine omega t, okay, plus 2K2L of y cosine omega t, okay, and then we have plus 2L f naught cosine omega t plus me omega squared sine omega t, okay? So let's group our cosines and sines together. So this becomes equal to, I'll put the cosines first, 2K2L plus 2L f naught cosine omega t plus 2C2L, this is actually negative omega y, I'm missing something here, I'm missing this y, okay, and then let's make the notations the same order, so negative 2C2L omega y, okay, plus me omega squared. And this should have an L here. I'm sorry, I must be really tired to make these types of rookie mistakes. There. Okay, there's my L. I must have dropped it there. Did I drop my L anywhere else? Okay, just there. Okay. Omega squared. And then I need the space back. Squared L times sine omega t. Okay? So it's a little bit cleaner. So now we're going to, I don't want to have to rewrite this whole thing over and over and over again. So we're going to let d equal to 2k2ly plus 2lf naught. And we'll let e equal to negative 2c2 omega y plus me omega squared L. Okay? Okay, and now that whole system becomes equal to d cosine omega t plus e sine omega t. Okay, so now let's rewrite this our whole big system again, and let's simplify it down, right? So now we have c minus a cosine omega t minus phi plus b sine omega t minus phi is equal to, I gotta start writing closer together. There we go, because we want, there we go. Is equal to d cosine omega t plus e sine omega t. Okay? Now, this looks, we've dealt with this before actually. So if we go back in our notes, we dealt with this before. That was system 3. Where's our summary slide? Okay. Guess what? That was this system right here. All right, let's go back to system 3 and look at the way it ended up being. Okay. Let's see, did I write that intermediate step? But hey, this is the same thing. Okay. Why not? Those are just cosines and sines. Those are our cosines and sines. So we've actually done this exact problem before. We just called the variables a different thing. Okay, so now let's remember that cosine of omega t minus phi is equal to cosine omega t cosine phi plus sine omega t sine phi, and that sine of omega t minus phi is equal to sine omega t cosine phi minus cosine omega t sine phi, just to make sure I'm not wrong. Okay, let's go back in my notes just to make sure I'm not doing anything incorrect. And there we go. Okay. Yep, there we go. Okay. So we'll pull this to the next page. Okay. Okay, and let's do the substitution. And when we've already done the substitution, we know how it's going to turn out, but might as well do it again together. So we end up with c minus a of cosine omega t cosine phi plus sine omega t sine phi plus b times sine omega t cosine phi minus cosine omega t sine phi is equal to d cosine omega t plus e sine omega t. Okay, and now we're going to collect the cosine omega t's and sines in their own lines. So we have c minus a cosine omega t cosine phi. Okay. And then here's another, so minus b, here's another one, cosine omega t sine phi is equal to d cosine omega t. Okay, so here's one equation, and here's the next equation, c minus a of sine omega t cosine phi plus b sine omega t cosine phi is equal to e sine omega t. Okay? And then these terms, those get crossed out for each of those equations. And that simplifies to c minus a cosine phi minus b sine phi is equal to d. And then c minus a cosine phi. Wait a second. I have a mistake somewhere. I can't have sines twice. So this is sine phi. There we go. Sine phi plus b cosine phi is equal to e. Okay? So we'll label this 4 and 5 to be consistent with the other examples that we did. And then we're going to take 4 squared plus 5 squared and set those equal to, so add those two equations together. We're going to end up with c minus a squared plus b squared is equal to d squared plus e squared. Okay? Now, just to show you, because this becomes cosine squared minus 2bca. We've done this before. Look at the other examples and see how those all work out. But that's what we end up with. And now we can substitute in our c's, a's, and everything. Okay? So this becomes keq phi minus omega squared meq. And I think... is there an L in there? What was our... Nope. Okay. Minus meq phi squared plus, and this was omega squared ceq phi, or not phi, capital theta squared is equal. And I'm going to leave d squared and e squared alone. Okay? It's going to leave them like that. Now we can pull out our thetas. So our capital thetas times keq minus omega squared meq squared plus theta, capital theta squared times omega squared ceq squared is equal to d squared plus e squared. Okay? Now we can combine our thetas squares. So theta squared times keq minus omega squared meq squared plus omega squared ceq squared is equal to d squared plus e squared. And now we can solve for theta itself. That becomes d squared plus e squared divided by keq minus omega squared meq squared plus omega squared ceq squared to the 1/2. Okay, and if we try to get this into kind of a normal form, we can multiply the top and the bottom inside by 1 over k squared, and that becomes d squared over k squared plus e squared over k squared. Okay, divided by 1 minus r squared plus 2 zeta r squared to the 1/2. Okay, and now let's go in and substitute in what these d and theta is. So instead of, I'm going to pull these squares out over here. So theta equals 1 over k. times 1 minus r squared plus 2 zeta r squared. Oh, make that a little bit neater. Okay. And then, so the 1/2. And then let's look up what D and E were. Let's pull those over. Okay. In fact, let's just go and give ourselves a new thing. Okay, so this becomes capital V is 1 over K. I made a typo there. Yeah, just 1 over K times, this becomes 2K2LY plus 2L F0 squared. Okay. Plus negative 2C2L omega Y plus ME omega squared L squared to the 1/2, 1 minus r squared plus 2 zeta r squared. Okay. And there we go. Like that's pretty much how it turns out. So that was a pretty complicated looking system. But we could see that once we get MEQ and CEQ, KEQ, and then we substitute in, and we don't have to write this thing over and over again. We just call it D's and E's and A's, and look how it just simplifies really nicely to this form. And it's going to pretty much always simplify to a form like that. Okay. And then we could leverage that to go and design a system if we need to, or plot the system response. Okay. Okay, that's all I wanted to show you about that. At this point, now that you can generate your system equation, and you can see how those system equations are integrated into solving for positions in the response, there's very little you can't do in terms of analyzing and then eventually designing a system for a specific vibration response. Okay, thank you, everybody. I'll see you on Tuesday.